Hi everybody, welcome to Thermal Physics. Throughout this semester I'll be recording some online lectures to help supplement and help out students that might have missed class or want to refer back to some material that we covered in class and see it again. So without further ado then, let me launch into Chapter 1, Energy and Thermal Physics, and today we're going to discuss temperature. For those of you that aren't in the class that might want to supplement a class that they're taking somewhere else, what we're using is Schroeder's text on thermal physics. So if you want to refer to a textbook, that's the one we're using. So to start off, to define temperature, first a disclaimer, we're for real going to define temperature a little bit later. We're going to give the mathematical definition of temperature in a later chapter. But for now, we need a working definition to get started. And so the working definition for temperature that we're going to use is that temperature is a measure of the internal energy of a system. So it's one measure, there's others as we're going to see, but temperature is the measure of the internal energy of the system. Now, what is internal energy? Well, internal energy is energy that you really can't see with your naked eye. So, in other words, if you have a block of steel and it's 50 Celsius, then that's not going to look any different to you than a block of steel sitting next to it that's 100 degrees Celsius. To the naked eye, it looks the same. You can't look at this pencil and tell whether whether it's at room temperature or whether it's been outside in the really hot sun for a while. You just can't tell. Another working definition of temperature is that it's associated with how hot or cold something is. Okay? Now, our senses, particularly our sense of touch, provide us with a qualitative indication of temperature. But our senses are really not reliable enough. We can't distinguish between small differences in temperature just by touching or holding something. And of course, different people have different levels of sensation for how hot or cold something is. If you've ever been in a room with a group of people, they can never really agree on what temperature to set the thermostat at, for example. So we need a more technical definition of temperature than that. So for now, we're going to say that temperature is something that's measured by a thermometer, and we're going to deal with the true definition of temperature a little bit later. Now, we're going to talk about a number of different temperature scales in this class, and of course you have to deal with a number of different temperature scales in your everyday life. So the first one that I want to discuss is the one that we commonly use when the weather is reported here in the United States, and that's the Fahrenheit scale. Okay? This is named for Daniel Fahrenheit, who lived from 1686 to 1736. He was a Dutch, German, Polish physicist. First of all, he moved around a little bit, and of course the borders of countries were a little different in the late 1600s, early 1700s than they are now. Fahrenheit invented the mercury in-glass thermometer, and it was the gold standard for temperature measurement for a very long time. And this was invented in 1714, and he also developed a temperature scale that we still use today. The 0 point on the Fahrenheit scale was determined by an ice, water, ammonium chloride bath. Of course, ammonium chloride is a type of salt. Since when you add salt to something, it changes the freezing point, lowers the freezing point down. That's why the freezing point of the bath that contains salt at 0 degrees Fahrenheit was lower than the regular typical freezing point of water. So also on his scale, the temperature of plain water with no salt in it was 32 degrees Fahrenheit, and the temperature of the boiling point of water with no salt in it was 212 degrees Fahrenheit. He put 180 divisions or degrees in between these two standard temperatures that he used for calibration. He used 180 because it's a highly composite number. In other words, it can be divided into many different size divisions, and he thought that was useful. Another common temperature scale that we'll see and is used in weather reports in Europe and other places is the Celsius scale. And the Celsius scale was invented by Anders Celsius in 1710. Now, he developed this scale in a push towards finding an international standard scale. And he published on ways to calibrate thermometers at different barometric pressures in the interest of having a standard for measuring temperature that can be compared at different altitudes, for example, different weather conditions in different countries, and so on and so forth. So his scale sets the ice point of water, no salt, at 0 degrees Celsius and the steam point of water at 100 degrees Celsius. So he made it a base 10 scale, in other words. And then the length of the column between these 2 points was divided into 100 increments that he still called degrees. Now, it's interesting to note that Celsius did all this work in temperature and thermodynamics, but one of his primary interests was in astronomy, and he actually founded an astronomical observatory in Uppsala, Sweden, that still exists today. The conversion equations for converting from Celsius to Fahrenheit are shown here. The temperature in degrees Celsius is equal to 5/9 times the temperature in degrees Fahrenheit minus 32. And you can invert that equation. The temperature in degrees Fahrenheit is 9/5 times the temperature in Celsius plus 32. And you can use that to convert back and forth between these two different temperature scales. Now, I'd also like to go ahead and make some other important definitions that will lay the foundations for the rest of our time in this class. So first, I want to define what thermal contact is. So two objects are in thermal contact with each other if they can exchange internal energies in between them. So the exchanges that we're going to focus on will be in the form of heat or electromagnetic radiation. Now, this energy is exchanged when there is a temperature difference in between these two objects. Or another way to think of it is, if they're at the same temperature, they're still exchanging energy back and forth, but there's no net exchange of energy when they're in thermal contact. If there's a temperature difference between the two objects, what will happen is the hotter object will transfer internal energy to the cold object spontaneously. If you want it to go to the other way, if you want the cold object to give energy to the hot object in a net fashion, then you have to supply energy or do some work to get that to happen. It doesn't happen spontaneously, as we'll discuss more when we discuss the laws of thermodynamics. Now, it's important to note that objects don't have to be in physical contact to be in thermal contact. So, for example, we get a lot of energy from the sun, and that energy is transferred via electromagnetic radiation from the sun to us. But we're very far away from the sun, so we're not in physical contact. Thank heavens, or we'd be a big ball of soot by now. I'd also like to define thermal equilibrium. So thermal equilibrium is a situation in which two objects wouldn't exchange energy by heat or electromagnetic radiation if you did place them in thermal contact. In other words, objects are at thermal equilibrium when they're at the same temperature. Now, it takes a certain amount of time for two objects that are not at the same temperature, that are not in thermal equilibrium. It takes a certain amount of time for them to come to thermal equilibrium. So if you place a hot object in thermal contact with a cold object, eventually they'll come to a common temperature in the middle and be at equilibrium. But that'll take a certain amount of time, and that time is called the relaxation time. Now, you can change the relaxation time by changing how the objects are placed in thermal contact. For example, if they're in physical contact and you make the contact bigger or better, then the relaxation time will shorten. You can make the relaxation time longer by placing insulators in between the two objects, thermal insulators between the two objects. Kind of like you use coolers to keep your food cold when you're out in the sun, but eventually the food will get hot. It might interest you to know that there's not just thermal equilibrium, that there's other types of equilibria that we're going to be talking about throughout this course. So in addition to thermal equilibrium, there's also diffusive equilibrium and mechanical equilibrium. Diffusive equilibrium is kind of what you see when you have a cup of coffee and cream, and you pour your cream into your coffee. Eventually, what will happen is that the cream will diffuse all throughout the cup, and it'll be a nice milky brown color uniformly. If you want to hurry that up, you can stir it and force the cream to spread throughout the cup of coffee, and then it happens much faster. Another example would be air. Air is generally a blend of about 80% nitrogen gas and about 20% oxygen gas, and then there's some other trace amounts in there. If you have a sample of air from a room, though, if you took a sample over in the upper left corner and the bottom right corner of the room, they would contain roughly the same percentages of oxygen, nitrogen, and other trace gases. In other words, air has come to diffusive equilibrium, so you're not going to have a whole corner of nitrogen and a whole corner of oxygen. It's not going to happen that way. You also have mechanical equilibrium, and this occurs when the pressure equalizes. If things are not in mechanical equilibrium, then you can get big deformations, physical deformations. For example, if I had a balloon and I placed my balloon inside a vacuum chamber, then the balloon would expand out, okay? So it would cause a mechanical change in the balloon, right? But if, for example, the balloon pops eventually, then the chamber will come to mechanical equilibrium. No more gross motion, and the pressure will equalize. Now, temperature can be also thought of as the property that determines whether an object is in thermal equilibrium, or whether it's something, you can also think of it as something that can be measured with a thermometer. Now, how do thermometers work? Well, for example, you have a thermometer. You calibrate that thermometer by submerging it in different baths of substances, like an ice water bath or a boiling water bath. You calibrate the thermometer that way. Once the thermometer is calibrated, you then feel confident that if you stick it in an unknown substance, that you're going to have a correct temperature reading. So another way of stating that is, if two objects are in thermal equilibrium with each other, then they're at the same temperature. If two objects have different temperatures, they're not in thermal equilibrium, right? So what I could do is, if I have one ice water bath, I measure the temperature of that, then I know that if I stick it in a different ice water bath, it should be at the same temperature. And it's this principle that allows thermometers to work. Now, thermometers, of course, are devices used to measure temperature. Different thermometers might have different shapes and sizes composed of different things, and that's because thermometers are based upon the principle that some physical property of a system changes as the system's temperature changes. These properties can include the volume of a liquid, like in a mercury in glass thermometer or an alcohol in glass thermometer. The dimensions of a solid, like in some of those old school oven thermometers that are bimetallic strips where you have a coil that winds or unwinds. The pressure of a gas at constant volume, that's one that we're going to talk more about a little bit. The volume of a gas at constant pressure. A really common one these days is to use the electrical resistance of a conductor, a thermistor in other words. Or you might have seen these on the sides of fish tanks, the color of an object. If you stick a sticker on the side of your fish tank, the sticker will change color sometimes as the temperature of the fish tank changes. So you might have seen those kinds of thermometers out there. Here is the mercury in glass thermometer, invented, of course, by Daniel Fahrenheit. Okay? And that material in that capillary tube will expand as it's heated. Now, all thermometers have limitations to them, and you have to calibrate different thermometers, because the physical property that changes for any given thermometer might not change in the same way or at the same rate as a thermometer with a different physical property. So what you do to calibrate your thermometer is you have different baths that you submerge the thermometer in that have a known temperature. Now, the reason that works is because systems that are undergoing a phase change will remain at a constant temperature until that change is finished. So that's how these baths work. So for example, a bath of ice and water, a mixture of ice and water, is going to remain right at the freezing point once it comes to equilibrium. And it'll stay that way until all the ice in the water melts. Okay? So that's the ice point of water. And of course that occurs at 0 degrees Celsius or 32 degrees Fahrenheit at sea level. Now, boiling water remains the same temperature until all the water boils away. And this is called the steam point of water, which is at 100 degrees Celsius or 212 degrees Fahrenheit at atmospheric pressure. So you can use things like that, points like that, of objects that are going through a phase change to calibrate your thermometers. Now, like I said, there's going to be problems with different thermometers. Not all of the properties that we discussed, the volume of a liquid, the volume of a gas, color, resistance, not all of those things are going to change in a linear fashion over a large enough range. And that causes sometimes your calibrations to be difficult. And if the thermometers are different shapes, sizes, or use a different physical property, then the discrepancies between the thermometers are going to be especially large, especially when the temperatures being measured are far away from your calibration points. Now, physicists in the late 1700s and 1800s understood this. For example, they knew that mercury froze at minus 39 degrees Celsius, and alcohol boils at 85 degrees Celsius. And so if you're going to build a thermometer based on those properties, you've got a certain temperature range that that thermometer will work in. Because of this, physicists at the time that were doing cutting-edge research in this field liked to use a constant volume gas thermometer because it was more predictable and very experimentally reliable. Now, back in the late 1700s, early 1800s, if you wanted to be a physicist working in this field, you had to be a glass blower too, or at least know one. So here's a diagram of what a constant volume gas thermometer might have looked like back then. And you can still build these today, of course. So what you have here is an enclosed glass bulb, and it's filled with some sort of gas. Here the gas shown is air, but it doesn't have to be air. Then there's, to the bulb, you've got a tube coming out that's fixed, and then ends here in another larger diameter tube. Now, that's where the glass ends, and then you have a plastic tubing that then attaches it to another glass cylinder that you see over here. Now, the glass cylinder on the far right here is mounted so that it can move up and down, all right? Now, these glass tubes and the flexible tubing are filled with something like mercury, okay? What happens is, let's say that you calibrate your constant volume gas thermometer by sinking it in an ice water bath. All right, what you do to calibrate it at that point is you mark the level of the mercury here on the left. Now remember, mercury is filling this left-hand side of the tube, goes through the plastic tubing, and goes all the way up to the right, okay? So you mark the level of the mercury in your calibration bath. Now, you take your thermometer and you put it in a boiling water bath, and then you move this movable tube on the right-hand side, you move it up and down until the mercury returns to the X that you've placed, or the mark that you've made, indicating where it was in the ice water bath. Then you know what the height is that you had to move the tube up and down. That gives you the pressure change inside that air bulb. And then you can change that into 100 divisions in between and mark the temperature off, okay? So that's how these constant volume gas thermometers worked. Now, physicists were using these all over the place as thermometers and marking it off. Now, what they noticed was that the slope of the lines that they created, because of course it's a linear calibration of pressure with temperature, what they noticed is that the straight lines created all had different slopes depending on how they constructed their constant volume gas thermometers. That wasn't unexpected, but that the intercept over here on the temperature axis all came to what seemed to be around the same temperature. So this temperature, we later found out, turned out to be minus 273.15 degrees Celsius. Now, it took William Thomson, the first bearing Kelvin, it took his work to realize and measure for the first time what this temperature, which he coined absolute zero, really was. So William Thomson was the first physicist to say, hey, this is at about minus 273.15. I think his first reporting of the temperature was actually minus 269 degrees Celsius, but for the time it was a very accurate determination of the temperature of absolute zero. And he coined the term absolute zero. Some interesting facts about William Thomson. He's an amazing physicist, a British physicist. He did work in a lot of different areas, published hundreds of papers on different topics in physics throughout his life. He was actually knighted by the Queen of England in 1866, so he became Sir William Thomson in 1866, for his very important work on the first transatlantic telegraph project. He noticed that, or he pointed out that, the type of copper used in the purity of the copper used in the cables was very important, and he also pointed out that the bandwidth of the cable was limited by the diameter of the cable. So he did a lot of important work there. Later on, in thanks for all his work throughout thermodynamics, which greatly impacted the field, he was ennobled in 1892 for his work on that, and he became Baron Kelvin. Anyway, he was, again, the first person to make an accurate determination of the temperature for absolute zero, and he wrote one of the laws of thermodynamics in one of the forms of the second law of thermodynamics, which we'll discuss later. So this absolute temperature scale that he developed, we now use as the SI standard unit for temperature. It's an absolute temperature scale. Of course, it's known as the Kelvin. And absolute zero is the 0 point or the basis of this absolute temperature scale. He made sure that the change in the degree sizes was the same as the Celsius scale. So a delta T of 1 Kelvin is the same as a delta T of 1 Celsius. And to convert between Celsius and Kelvin, you just add or subtract 273.15. So that makes it nice and easy. Here's some examples of different temperatures on the Kelvin scale. You might be proud or horrified to note that here on Earth we've actually exceeded the temperature of the interior of the sun with our hydrogen bomb testing. There it is. Anyway, and the interior of the sun's about 10 to the 7th, the corona is about 10 to the 6th, the surface of the sun is a few thousand Kelvin. And then we get down into everyday temperatures, of course, where water freezes, and then liquid nitrogen, liquid hydrogen, liquid helium is 4 Kelvin. And then the lowest temperature that we've ever achieved in the laboratory, thanks to laser cooling and trapping, is 10 to the minus 9 Kelvin. So all some interesting stuff there. All right, that concludes the introductory lecture on temperature and temperature scales, and I'll see you next time.